we actually divided the lectures into undamped and damped. But at the end of the day, if you know to solve a damped free vibration, then you can solve the undamped because it's a lot easier. An undamped situation is the simplest model where your C is equals to 0. So in this case, we give you the overall for damped cases. And if you remember, under chapter 2, we have to identify the cases. Okay, if your zeta is less than 1, so which case are you looking at, class?
Under them.
Under them, yeah. So if your zeta is equals to 1, then it will be
Critical them.
critically damped, yeah. If it's over, so it's easy. So normally students ask me, how do you actually memorize this? If it's more than 1, so it's over damped. It's less than 1, it's under damped. So a lot of cases in real life, your zeta would be less than 1. So you probably gonna need to use this equation, a lot of these equations, yeah. And another important things, other than once you identify your zeta, then you also you need to identify the cases. So once you do that, you can use this equation. So if I ask the problem is solve the response of the system, okay, for free vibration, so you go ahead and check the zeta first. So whether you need to use this xt or this xt or this xt, and then using initial value, like if you have v naught x naught, then you can actually use the equation. I think you can see the cursor, right? It's a bit slow, maybe the response. So you can actually see if you have initial value problem, then you can actually look at this, yeah. And then end of chapter 2, we talk about logarithmic decrement. So basically you want to find the delta, okay. So in real life, I mean, you don't really have a mass spring damper system, okay. It's quite similarly what we're going to talk about today. This is chapter 3, harmonically excited vibration. You don't have a nice mass spring damper system. In real life, it can be in the form of machines, it can be in the form of a bridge, buildings, all the things in this world, you can actually model it as a single degree of freedom system. So you have to look at it after that, whether it's a forced vibration or a free vibration. So if you have a forced vibration, we're going to take a look at in chapter 3. So this is all about chapter 3. We're going to take a look at about 3 cases, what we call fixed based, okay, and then we have base motion. Okay, the second case is base motion, and then you have rotating unbalance. So those are the 3 cases that we're going to take a look at chapter 3. So far, for lecture 6 and lecture 7, I think I've explained that, where lecture 6 is for undamped, where your C is 0. Okay, lecture 7 is when your C is not equal to 0. You're gonna watch the video after this for lecture 7. I also mentioned yesterday, basically, if you have input of f naught cosine omega t, then your output will become cosine omega t as well. So let me just stop this for a while, and maybe it'll be easier if I show you from kind of confused whether to use the tab or the desktop. Let me just share screen. Hold on, yeah. Okay. All right. So basically, okay, maybe it's easier to have the tab. So basically, if you have this, as I said yesterday, if you have the input is cosine, the output is cosine. And notice that in this list of equation, all the systems are linear system, yeah? So there's no rotational. So if it's rotational, okay, if it's rotational system, you may want to jot that down in your notes or your list of equation. If it's rotational, then everything will change into rotational. So for example, how does your EOM looks like for rotational class? Can you tell me? Class, are you with me? No response?
Yes, madam.
Yeah,
Theta
J,
dot,
theta double dot, come on.
C,
Class?
C theta,
C
secant
theta
dot.
dot.
Yeah, let's say we want to differentiate that C with C torsional or rotational. So you have CT. So all your X will become
Theta.
theta. Yes. And all your K and C are all rotational or torsional. It's the same. Sometimes we use it interchangeably. So everything will change. So what happens to force? What would that be? If J theta double dot, it will be summation of force, summation of
Moment.
moment, isn't it?
Yeah.
Yeah, for free. But for harmonically excited, so you would have moments. So take note of that. It's not in the list of equations. So you need to know how to go from linear to rotational. So same as all these parameters, you know, these xt will become theta t. The capital X will become what? Will become what, class?
The capital theta.
Theta.
Yeah, capital theta. So this is how it looks like. Yeah. So the response, the displacement or the response now is not in X, is in theta. And the amplitude is not capital X, but it's capital theta. Okay, so what about your the amplitude? What about the amplitude now? How do you write the amplitude?
Capital
So it becomes
theta
capital theta, okay, equals to
equals to moment.
Moment. M.
Moment.
moment. Yes, very good. So then divided by, you have what? Your KT.
Okay.
So your M become
J.
J.
J. Okay, very good. And then you have your omega, a square, everything square, plus C omega square. Okay, very good. So please take note of that and make a note that everything in these equations will change if you look at the rotational system. Okay, so for lecture 6 and 7, basically these are the main equations that you're going to use. The rest you're going to take a look at next week. So let me just show you an example of lecture 6. How do we solve this problem? This is actually problem 3.24. You are asked to derive the equation of motion and find the steady state response of the system, okay, as shown in figure, given in the figure. Yeah. So in this case, you can see that what they ask you is steady state response. Anybody wants to tell me what it means by steady state response? What do you want to find, basically? Class? What variable is it? If I say steady state response, what variable is it? No idea. This is rotational. Okay. It's actually what you want to find is your theta t. If it's linear, when I say steady state response, what do you want to find?
XT.
XT.
XT. Okay. So when you read the problem, okay, you have to understand how do you, when you read the problem, you have to understand what is the variable related to it. Okay, or for example, they say find the response. Response means output from the system. Response means X or theta. Okay, depending on the type of system. So this is rotational. So you can see that the theta goes this way, okay, which is clockwise. Okay, so you have the movement of theta. So how do you actually draw the free body diagram? So because you want to find EOM and the steady state response. So there are before EOM, what do you need to do? You need to do free body diagram. So these are the things that you need to do. Okay, so first of all, how do you draw the free body diagram? Remember the steps that I told you in few lectures before as well. The first step is you always draw on the spring. Okay, don't straight ahead draw on the mass. I think it's quite common for all the students. They always draw straight on the mass. Okay, you always draw physical forces on the springs. Okay, if you look at this, that's why in mechanical vibration everything is physical. Okay, no abstract things like when you learn electrical. In mechanical, a lot of things are physical. So you think of it physically. What happens if you have this bar going downwards? Yeah. So if it actually goes downwards, okay, let's say I do a simple skeleton to draw the free body diagram. So it will go like this, isn't it? Because your theta is like that. So think of physically, what happens to K1 and K2 class? So what K1 is somewhere here. Because you don't want here, your J and your M is the bar and the mass. Okay. So basically, your mass is still here. Okay. So you don't want to draw on the bar and the mass first. Then you draw on the spring. So your spring is here. Which way is the arrowhead here? Which way is the arrowhead here?
Upwards.
Physically, you look at the direction.
Physically downwards. Downward.
Yes, that's why I say you have to think physically, yeah, downwards. And what about K2 over here? K2 will go
Downwards.
downwards. Okay, so you have this K2, you have this K1. So then only you draw, you draw action, reaction on the bar. So the mass or the J here is actually the bar. All right. So then you have to remember, if you have this kind of problem, it is basically quite similar to your triangle because this is a single degree of freedom system and your displacement is actually theta. There's only one displacement describing it. Whereas your K1 and K2 are linear. Okay, what is the displacement if it's a linear system? It's actually x, isn't it? So if you want to write the force of a spring, it's actually kx. So you will want to change it in terms of theta because everything is theta. So do you remember the theory or trigonometry that we talked about last time, which is you have a kind of like a small triangle that describe, if I call this, the force here is K1x1. So basically, if you draw from here to here, okay, so I just bring it somewhere here. So you have O. This is the pivot point O. Okay, it's the same. This is displacement of K1, which is x1. This is theta. So this distance here, if you look at the problem, is what? Is A. So you have for K1, okay, can you understand the figure? So for K1x1, you're supposed to write K1x1, but you want to relate what is it in theta. So what is it in theta, class? What do you get then? K1?
K1
to
theta 1.
omega.
No, in terms of theta.
K1 torsion
X equal
This
to
one
A
theta
omega.
1.
is A. No, K1, what is it in terms of A? Remember this equation? X1 is equals to what? If you have this triangle.
R theta.
A sin
X1 is
theta.
equals
A sin
R
theta.
theta.
Yeah, okay. I know it's a sine theta, but we have introduced this in the beginning of lecture 1 earlier. All the theta are small, so sine theta is equals to theta. So you just use the equation of x1a theta. Okay, it's just like your S equals to J theta. J tu jejari kan kalau belajar masa sekolah dulu. Or R, R theta. So basically the general equation is actually X equals to R theta, isn't it?
Yeah,
So-
excuse me. Madam.
Yes.
So
Yes.
basically the spring will move in in transverse, vertically, but then we convert it into theta forms in terms of theta.
Yes. Yes. Your force is actually K1x1, but you want to write everything in theta because your displacement here is theta. And what you want to find is in theta. So you have to convert everything in terms of theta. So the way to write your force is K1A theta. Okay.
Okay, thank you, madam.
Any other question? No?
No, thank you, madam.
Welcome. So it's easy, isn't it? Once you know this theory, is always this kind of problem is always x equals to r theta. Yeah. So once you know this theory or this trigonometry, then you can straight ahead write. You don't have to draw the small triangle anymore. So what about K2 then? How do you write K2? Supposed to be K2x2, but your x2 is equals to, what is the distance here?
B theta.
Yes. So then basically the force here is actually K2 B theta. Okay. So don't forget, you also have your F naught here. I forgot F naught. You cannot do anything lah. Is because it's actually the force, external force. You don't change anything. There's no but you have to remember. After this we're gonna write everything in terms of moment. Okay. Are we done with our free body diagram? Class, do you think we're done with our free body
The
diagram?
mass.
Not yet.
Not yet. The mass.
The mass? Yeah, the mass is there.
Mass for
We put F naught.
bar and
Yeah, the free body diagram. Actually, we've done with the free body diagram. Free body diagram means all the action reaction forces on the bar. Okay, so the mass is there. Yeah. Okay, so how do we write the equation of motion? So let me just erase this part here maybe. Then we take a look at the EOM. So for this case, okay, we're gonna write all this n mass, everything in terms of moment and also all these forces. Okay, so the general equation is basically J theta double dot, okay, because this is rotational system, equals to summation of moment, and you have to identify the positive direction of this. What is the positive direction, class, in this question?
clockwise.
Clockwise. You have to follow the question. If positive, if the question doesn't give you any direction, that's the first thing you need to do. You have to assume the direction either clockwise or counterclockwise. That's the first thing you need to do. So that's what happens in the final or in the test. You have to assume the direction if it is not given, so that we understand your plus minus refers to which direction. So in this case, they already give you the direction, so you need to follow the direction. Okay. So here we have your J. So what it means by J is the is actually J naught, okay, with respect to this pivot point O. Okay, so in this case, although we have J naught theta double dot, you can see there are two masses. One is the mass from the bar, and you also have the end mass here, okay, which is actually, if you write it in terms of moment, you remember the moment of inertia of end mass. So basically, you have to write it in terms of ml square. Okay, maybe some students, they ask, what where do you refer to get your J naught? So J naught is basically moment of inertia with respect to your pivot point O. In this case, the normal moment of inertia, normally you have to get it from a standard table. So if it's in the test, normally we give it to you. If it's in textbook problem, you can find it in the textbook. There is a table where you can find the J naught. Okay, I'll explain that later. So basically in this case, this M, the moment from the M already taken care of basically, and it actually combines together. Then we have to write in terms of our moments, yeah. So in terms of our moments here, we have two other force, basically three force. You have this. So remember, when you want to write the EOM, you are referring to the bar, okay, and this system. Yeah, you are no more looking at this K2 and K1 in that you started off last time. So you just look at the action reaction forces on the bar. So you have 1, 2, 3 forces. Yeah. The first one is the K1. So you just write what is the direction of this force here. Maybe I color it a little bit so that you can see. So this force here is going up. So you go from that point to the direction like that. Okay. So what is the direction then? For K1A, maybe I write like this. You have, is it negative or positive? K1A theta.
Negative.
Okay. It's negative because it's counterclockwise. Okay. So it's negative, but don't forget, this is force. This is force, yeah? So you have to times what? You have to times distance.
Distance.
What
A.
is it?
A.
Okay. So this is your distance. So then we do the same thing for K2B theta. Is that negative or positive? So you go from the pivot point to the arrowhead like that. Counterclockwise or clockwise? Counter, right? So this one counterclockwise. This one also counter. Is it
Counterclockwise.
true? So you also get a negative, right? So you have K2B theta times what?
B.
B. Okay, so maybe first time I label everything, but I think as you go along, you may know how to do it. Okay, one more. You have external forces, right? F naught. So that should be going from the pivot point, you go to the arrowhead. Is that positive or negative?
Positive.
Yeah, so it's positive. So basically you have your, okay, that one is a positive, but don't forget you have to times what? F naught times the distance is
L.
L. Yeah. So it's always that the distance is always based on the pivot point. Yeah. O. So the distance is L. So you get you just write it down, sine omega t. So basically force times distance. So you done with the EOM. Okay. But of course you need to shift. So the normal model is basically you have to write everything on the left hand side and leave the input to the left hand side. Okay, so what you have is basically you have your J bar plus ML square J naught bar, I call it. Okay, theta double dot. So everything negative will go to the other side of the formula. So you get K. So you have to collect all the terms. So you have K1 A square plus K2B square, everything theta. Okay, are you with me? Which is equals to your F naught L sine omega T.
Madam,
Yes.
can you explain back how you get J bar plus ML square from the J naught?
This is the equation is basically J naught. Okay, J about the pivot point. We haven't solved for J naught bar. That is another story. After this, I explain. But this one, sorry, this is capital M to represent this capital M.
So J naught consists of
Yeah.
J naught bar plus
To the
ML
bar
square.
because there are two masses, and this one is due to the mass at the end.
Okay.
Okay.
Where does the L square come from?
Oh, this is a formula for moment of inertia when you have a mass at a distance.
Okay.
Yeah. So normally in the test will give it to you if you know if it's like this. So it's actually that's the equation. Moment of inertia when you have a n mass at the end. Yeah.
Okay, got it. Thank you, madam.
Yes. Okay. So then you can see that now it is in the form. What you need to pay attention here is basically it is in the form of this is what we call the J equivalent, because you remember your model, you have J naught theta double dot. This is undamped because lecture 6 is still undamped. KT theta equals to moment sine M naught, sine omega T. Okay, so basically this is your J naught equivalent. Okay, I want you to understand how to use the equation, basically, and then this one is your K torsional equivalent. Okay, and then this one is basically your M naught. Are you with me? Because we are referring to this equation basically. Okay, are you with me?
Yes, madam.
Yes, madam.
Okay. So after that, because they ask you to find the response, so you need to use all these values. Okay. So remember I showed you the response equation. Then you have to substitute all the values in it. Okay. Let me just also explain your value, the J naught equivalent here. Okay. This is another story about how you find your J naught bar. If you look at or refer to your moment of inertia, I think you learned in your previous statics about moment of inertia. Okay, when you have a bar, it is at the center of gravity. Okay, you can straight ahead go to a table for a bar. Moment of inertia of a bar at the center of gravity is given by 1/12 ml square. So, however, where is your pivot point here? Is it at the center of gravity or no? Where is
No.
your pivot point here?
At the end of the bar.
Yeah, so your center of gravity is here, basically in the middle, which is L/2, isn't it? Because the total distance is L. Your center of gravity is at L/2. So what will be the distance? The distance between the pivot point to the center of gravity is, what is the distance? What is the distance?
0.5.
L over
L
2.
2.
Yeah, they give it to you the values, right? Which is 1 meter. So then you have to divide by 2. So when you have this case, when your center of gravity does not coincide with your pivot point, then you have to use another formula to find your J naught of the bar, which is equals to J center of gravity plus MD. M is the mass of the bar, MD square, where your D is actually the distance of your pivot point to the center of gravity. So this is your basically your D. Okay, so what do you get if you actually do that? So J at center gravity of a bar is 1 over 12 ml square, and then you have to plus mass of the bar times D. Your D is L over 2. So what do you have? L square over
4.
4. Okay, so if you substitute that, you will get 1 over 3 ml square. Okay, so ini baru J not bar lah. Then but at least you have all the values there. Then the next step, so you have all the values in the question, isn't it? So you can actually substitute into the equation and solve for your first of all. So once we get this is the EOM, we already have the EOM here. Then you can solve for your capital theta. So tell me what is the equation for your capital theta? Class? I already explained that in the list of equation just now. Your capital theta is equals to, in this case, you have to match. You have to match all this using that equation. So basically you have what? It's supposed to be M naught, right? So here your M naught is F naught L. Okay, where did you get this equation from? See the list of equation just now that I showed you. In the list of equation, which equation you look at?
The capital X.
Yes, the capital X. Okay, very good. So you have F naught L. Okay, what about your K? Supposed to be K minus M omega square, isn't it?
Yes. Square.
Yes. So now it's not that. You have to use all the equivalent values here. Okay. So what do we have then? What is your K? What is your M? What is your omega? Your K is?
K torsional. K equivalent. K torsional
Yeah,
equivalent.
the K equivalent, which is K1A square plus K2B square. So that would be your K. Okay. So then your M. So your M is not your M. A lot of students make this mistake. So your M will be?
ML square.
Your M will be the whole thing. Yeah, alamak. Okay. Your M will be this whole thing. Your J naught bar plus ML square. Yeah. So you have your J naught plus J naught bar just now plus ML square. Okay. J naught bar tadi we already have this value. Yeah. So you have to substitute and then you have your omega square. Okay. Are you with me? So
Yes.
yeah, so basically you have all the values. You can find your capital theta. Let me just cut short a little bit because of the time constraint and you need to do your quiz in a while. So if you substitute everything, okay, you can go back and try this out. So basically your capital theta, what is the unit class? What is capital theta unit?
Radian.
Yes, it should be in radian. Okay. So then you can easily write your small theta, which is the response. So the final answer should be in terms of small theta. So you just write your capital theta here. Okay. How do you write? Yeah, because input is sine. So you
Output is
write
sine.
it. Yeah, output is sine. So what about omega? It's the same omega, isn't it? What is the omega value? So you look at, can't remember the omega, 1000 RPM you have to convert, isn't it? So you have to convert berapa omega dia? 104.72 if you convert that. So they give it to you 1000 RPM. So you have to convert the omega. I think the omega should be 104.72. Yes, radian per second. So you write here 104.72 omega t. Okay. So that is actually the final answer where you are asked to find the response of the system. Any question? Any question? So remember today you're going to have a quiz which is based on lecture 7. This problem is lecture 6, but I think the process is quite similar to the quiz. The difference between this problem and the quiz is basically